The broadcast is now starting. All attendees are in listen-only mode.
Okay. Good morning, good day, good evening, whatever it is to you. Welcome to the Vibrant Technology monthly webinar. Today we're going to cover what was advertised as advanced curve fitting. More specifically, we're going to talk about multiple reference, or what we call multi-reference modal parameter estimation or curve fitting. So I'm Mark Richardson, the president of Vibrant Technology. We're broadcasting from Scotts Valley, California. It's raining this morning. It's 8:30 in the morning, and we're very happy because we need more rain in California. You know the song that it never rains in California? It's been true here the last this past winter months. Anyway, Brian Schwartz is with me. He's kind of the technical guy behind the scenes of this webcast, and near the end, time permitting, we're going to allow you to send him emails, and we will answer your questions. We've got a lot of material to cover today, so I'm going to go rather quickly, show you several examples of multi-reference curve fitting, and then hopefully we can get through a lot of this material in the next hour. These are some slides that we use when we teach class here at Vibrant. We have a 3-day class coming up here next month, but I just want to go through a few of these slides to introduce what we mean by multiple reference curve fitting or modal parameter estimation. As you know, this is a critical step in the use of broadband FRF-based data to identify the modes of a structure. So this is what we mean by curve fitting. Here's an FRF in 4 different formats. On the left are the real part and the imaginary part of the FRF, and on the right are the phase above the log magnitude. Sometimes the left hand is referred to as a coquad plot, that coming from the old days of sign testing, where we talked about the coincident and the quadrature wave, that being the real part and the imaginary part of the sine wave. The one on the right is often called a Bode plot. Now, Bode was a guy who first started drawing these plots by hand, and typically it would be a log magnitude, log frequency plot. Here we have log magnitude linear frequency, which we normally use in modal analysis for during curve fitting. So what you're looking at here is data, the blue line, which is pretty well covered up by the red lines. The red line is what we call a curve fit function, and it's been matched to the experimental data in what we call a least squared error approximation. So the red line is an ideal waveform of an FRF, and during curve fitting, we match that ideal waveform to the experimental data, and in the process, we identify the unknown parameters of the analytical model, which are the modal frequency, damping, and the magnitude of the residue, or the magnitude of the numerator, which we call the residue. So we'll use that terminology a lot here, but just think of the residue as a constant term in the numerator of the FRF, and there's one constant for each mode of vibration. Okay, so these are different curve fitting methods that we have available in ME-Scope. they kind of go from the simple to the more complex. Now, in previous webinars, we covered the first three methods. When we talk about local SDF, what we mean there is one mode at a time, single degree of freedom. So the curve fitter is working on one mode at a time. Local MDOF means that we are simultaneously identifying parameters of many modes, but local means that we are getting frequency, damping, and residue for each mode in each FRF. Global curve fitting, which is we're going to use today, it's the most popular one that we have with MeScope, does two curve fitting steps. First, it curve fits all of the FRFs to obtain frequency and damping, and then secondly, using the frequency and damping estimates, does a second curve fit to get the residues. Now, the residues are assembled or saved into a shape table, and those are the mode shapes. Multi-reference or polyreference curve fitting, what we're going to talk about today, uses multiple references of data. So I'm going to explain that here in a minute. And it is useful when we have a situation, or we think we have a situation of closely coupled modes. In other words, the resonance peaks in our data only show evidence of one mode, but in fact there's two or more modes there. And then a more extreme case called a repeated root, where we have two modes with different mode shapes but exactly the same frequencies. So we'll look at both of those cases.
Okay.
So here are the two reasons why we want to do multiple reference curve fitting. To identify two or more closely coupled modes, and yet there's only one resonance peak. And then the second case is more severe, and that's what we call repeated roots. And this happens with, we're going to look at a disk structure, a circular symmetric structures will have two modes at exactly the same frequency, but actually they have different mode shapes. Okay, here's what we call a transfer function model. Now, this is a more general purpose model, and we use the word transfer function, and we think of a structure as a black box that has so many inputs applied to it, and then the transfer functions multiplied by the Laplace transforms of the inputs gives us Laplace transforms of the output. So that's what we mean when we indicate here in the math. Over here would be a force number 1 as a function of the Laplace variable or complex frequency variable. In the transfer function matrix are, again, complex valued terms. We looked at earlier what one of these looks like in an earlier slide. Here it's a function of the complex frequency. And then over on the left-hand side is the response as a Laplace transform. Now, we don't normally deal with Laplace transforms in modal because the Fourier transform gives us what we call frequency response functions. But this is the input-output model that underlies all of the work we do in modal analysis. Now, here is a more specific case, what we call a FRF model or matrix model. We also refer to it as a MIMO model, multiple input, multiple output model. Now you can see that the transfer functions have been replaced with functions of frequency only. And there's a j in there, square root of -1, so it's an imaginary frequency variable, as opposed to the complex Laplace variable or complex frequency variable, we now have just an imaginary frequency variable. These are called FRFs, a special case of a transfer function. These measurements we can measure with a Fourier analyzer and with our typical signal analyzer equipment. On the right-hand side over here, we've got the Fourier transform of the inputs, or the forces. On the left-hand side, we've got the Fourier transforms of the outputs, or the responses. So when we talk about multiple reference FRFs, what we're talking about are two or more columns of this FRF matrix. You can see here we just got 4 inputs and 4 outputs. In a general case, this model can fit any real-world situation where we have as many inputs and as many outputs as we make measurements between. So each of these FRFs is a cross-measurement between an input and an output. And there's various ways, we won't get into that today, that we build up rows and columns of this matrix. When we talk about multiple reference, though, we're talking about measuring 2 or more columns or 2 or more rows of the FRF matrix. So that's what we mean by multiple reference. Let's just take an example. If I had 2 shakers, I had one at 0.1 and I had one at 0.4. Well, that would correspond to measuring the first column and the 4th column of this FRF matrix with an FFT analyzer and all the signal processing that goes into measuring FRFs. Out of that, I would have responses for 1 through 4 points, response points. Those could be different points or they could be the same. It doesn't matter. But I've got 2 columns of data when I do a multiple reference, or let's say a multi-shaker test. Now we're going to look at an example here in a minute where we had 2 accelerometers mounted on the structure. So let's say that they're at 0.2 and at 0.3. They are fixed, and now we have a roving impact hammer that simply impacts at 0.1, 0.2, 0.3, 0.4. That would correspond to measuring 2 rows of this FRF matrix. The row corresponding to the accelerometer at 0.2, the row corresponding to the accelerometer at 0.3. Now these are just numbered points 1, 2, 3, 4. Typically what we add to that is not just the point number but also the direction of measurement, because vibration has direction associated with it. So this would be better labeled when we're taking this data as 1x, 1y, 1z, or 1z, 2z, 3z, 4z, depending on how we set up our test. Okay, multiple reference curve fitting. What do we mean there? Well, after we've collected this FRF data, we've got 2 or more references of data, either 2 or more rows or columns from the FRF matrix of possibilities that we can measure. And remember, that matrix can be as large as we want it. We just make more measurements at different points, different directions. So a reference DOF is the fixed excitation or response DOF. So if we got columns, we're talking about fixed excitation. If we got rows, we're talking about fixed response. Now, how do we go through an Emiscope to curve fit this data and get some modal parameters? First thing we do is we put up a mode indicator function, and we have 2 kinds in Emiscope. We'll look at those in a minute. One called CMIF, the other called MMIF. And then we can either count peaks on those functions or we can use the stability diagram. But those indicators are specifically designed to show us when we have closely coupled modes or repeated roots. So we'll look at that. The second step then is to basically do a global fit. Whether we're doing a stability diagram or the polynomial fit, we're going to use them both. We get frequency and damping first, and we use what are called modal participation factors to weight the various references of data. So if we've got 2 references, We use participation to weight that data when we go into the curve fitter. Then on the backside, when we come out, we use those participation factors to compute the residues, which again are the mode shape components, or the numerators of the FRF analytical model. Finally, we save each reference of data, and we can animate to look at the mode shapes. So here's a little more discussion of what these mode indicators are. They're very specially designed for use, and they work with a single reference as well, but they give us these modal participation factors when we have multiple reference data, both of these indicators. And we'll try them both as well as we'll try different curve fitters. Our philosophy at Vibrant is that these are tools in your toolbox. Now, other people will say, well, you only need one curve fitter, just buy ours, it's the best one in the world, it solves all the problems. We don't believe that. We think that depending on your data, real world data is going to have lots of noise in it, might have electrical noise, might have other extraneous things in there that you cannot get rid of, like order-related peaks and so forth. You need all the curve fitters that you can get your hands on, and then our approach is that you compare answers from different approaches, and here we can compare answers from the CMIF and MMIF and get a better understanding of how these mode indicators operate on different kinds of data. Okay, well that's enough. Let's go look at this example here of two closely coupled modes. I'm going to stop this and I'm going to bring up MeScope and we'll take a look at this this example right here. All right, here I have a structure, a very simple structure. It's a PVC plate, and you can see there's a bunch of points on there. Let me just start the animation and we'll just kind of look at some of this data with the animated display. Okay, immediately it's telling us that the following source has multiple reference DOFs, and it's listing the source. Select a reference DOF. So you cannot animate multiple reference data without selecting one of the references. That's basically what it's telling me here. Now, why is it doing that? Well, there's another principle at work here that I haven't mentioned, and that is that every row and column of the FRF matrix, and more specifically the residues for every row and column of the FRF matrix. Remember, the residues are the numerators of the FRF model, and each FRF and each mode has a unique residue. So if I showed you some more mathematics, the conclusion is that each row and each column of the FRF matrix has the same mode shape in it. So what we're going to do is the animation. We're going to look at animation here and see if in fact that's true for this data that we've taken, and we've got two references here. So let me go ahead and do that, and I'm going to stop the animation here and let's just look at the data here for a second. So let's get the data up here. All right, and we'll close that. So here are my measurements, and here's my spreadsheet here showing the measurements and some of their properties. I'm going to hold down the control key and zoom the spreadsheet a little bit with the mouse wheel, and you can see that I've got some selected. I'm going to unselect them. I'll turn this cursor off here, and I'll just scroll through this data. So you can see there's a bunch of peaks in here, and this is live data off of a PVC plate. And we've labeled this data so that it's got multiple references. Now, the way MeScope labels data is the first degree of freedom in this DOFs column here. Let me make it even larger so we can see it. Is what we call the roving DOF. So that could be either a roving impact or a roving, I see we're not all visible here either. Let's make them all visible. That was a visible column. We had one that was invisible. The first DOF is could be a roving impact or a roving accelerometer. The second DOF behind the colon is the reference degree of freedom. So you can see that we've got a reference here at 0.7 in the Z, and then down here there's some more data with a reference at 0.35 in the Z. So where are those points? Well, let's put this back down, and I'm going to pull this over, and we'll set this up. Well, where are those 2 points? Let's just turn on the points labels here, and we can see. So there's 0.35 and 0.7. In fact, I've got a substructure here that I made with some icons on it, just two of the points. And if I turn that on, there is where the 2 accelerometers were located. So this is a multiple reference test with a roving impact hammer at 35 points and then 2 accelerometers at 0.7 and 35. So that's the set of data that we collected off of this PVC plate, plastic plate. Now, when I start the animation, let me go ahead and do that. Okay, now it's telling me I have to choose a reference. So I've chosen a reference here. You can see my 2 choices are 7Z and 35Z. If I switch over, you can see that shape kind of changed there. Well, a good way to animate our shapes, let me turn off the point labels and the points, and I'll even turn off the little icons here. So we can just focus on the mode shapes. Now if I go down to DC, down to low frequencies, I see what I would call rigid body mode. So this is a validation of my data, my 35 points there. And you can see that I got node lines on, so they're kind of rolling around as this thing animates. If I switch to the other reference, I still have basically a rigid body mode. This is just the plate rocking on the foam. I come up here to the first peak though, and what is that? Well, it's not clear what that is. It's not what I'd call a bending mode. It's not what I would call a torsion mode. Let's go up to the next peak. Now that clearly is a torsion mode. That's a twisting of the structure, but it's what I'd call second torsion. It's a higher frequency than what I would call first torsion or first twist of a simple structure like that. When you test a structure this simple with no boundary conditions other than the foam that it's sitting on, you expect to see a first bending and a first torsion mode. We're not seeing it in this data. If I go up to higher frequencies, I see there's some bending. Now that's a complex shape. It's rather complicated. Let's switch over and just display the imaginary peaks. Okay, so there is a bending mode, but it's bending in the stiff direction. I expect to see a bending mode at a lower frequency in the longer direction or the less stiff direction. And if I go up here to these higher frequencies, I'm seeing even higher combinations of bending and twisting. So the problem is there. That is not what I would expect to see. Now let's take a closer look, and as you can see when I switch over to the other reference, the shape kind of changes. Well, there's another way to look at this. Let's stop the animation here for a minute, and I'm going to close this. I'm going to make a copy of this data, and I'm going to do a comparison display between the 2 references, and then we'll compare the shapes that we're animating using a modal assurance criterion, or the MAC calculation. So again, I haven't done any curve fitting yet. I'm just exploring this data to see whether, in fact, I have closely coupled modes or even worse, repeated roots. So let's let's make a copy of this. So I'm going to copy these traces to a file. All right, it's saying you got things selected. I want to unselect. And now I'm going to make a copy. So I'll just call this a copy. All right, so here's another data block with the same measurements in it. Let me put that over here, and I'll rearrange things. So now I've got two data blocks. One on the top is the PVC plate data, and the bottom is the copy. And now I'm going to start the animation and do a comparison display. All right, it's saying you can't just display this data without choosing a reference. And again, it saw the second set of data, and it said the same thing for that. So now I've got two little selector boxes here, and I'm looking at the two shapes animating out of the two different data blocks. Now they're both on 7Z. So they're both animating out of the same reference. We see the same shape.
The copy up top and the reverse relative to their data blocks. Just so that you...
Oh, these are okay.
Yeah.
Let me draw this down. Brian has interrupted me here and said that I've got my dialog boxes. Oh boy. Now, you see what happened there? Things kind of jumped around on me. We can leave this here. If I want to change that back the way I had it, I need to go here, show sources on right. So I opened up the structure options box. I'm going to cancel that, and let's get things back the way we had them here. Arrange for animation. Oh, that's not. Oh, I canceled. That's why. So let's just leave it here. And this is, see, the sources are below. If I select the sources on the right and then said OK, it would put them on the right. That's where they were originally. But now they're below. Let's just leave them there. And this one is the PVC plate. So this goes over here with the PVC plate. This one goes over here. These are our selection boxes. I'm going to do one other thing here. I'm going to, under Compare Shapes, I'm going to synchronize the frequencies. So if I move the frequency in this block, it's not doing what I wanted it to do there. Synchronize frequencies. Okay, now they're synchronized. So I had that already turned on. So now you can see as I drag the cursor in one data block, it's animating the shape from the other data block, and they're both animating off of reference 7Z. Over here on the corner, in the upper right-hand corner, is the MAC value, and you can see that it's at 100. Or 100% or a value of 1, that's indicating that these two shapes are the same. So we're animating the same frequency out of two data blocks, but now let's go over here to this frequency and let's change its reference to the other reference. Bingo. Now you can see that even though we're at the same frequency in both data blocks, and I'm going to put that cursor right back there on the peak. It's not finding the peak over here exactly. So what I'm going to do is turn on a peak cursor. So let's put the peak cursor on. And, wow, let's see. Peak cursor. Okay, I got peak cursor here. And now I have it in both places. So I'm going to narrow this down. See, the peak cursor is going to find that peak in both cases. And the line cursor sometimes is not accurate. But here you can see now the difference in those two shapes. Let me go over here and animate it this one. You see that That's the same shape, so that is a mode. This over here is an ODS being dominated by a mode, and this is evidence that there are two modes there. If I drag this cursor way over here to one of these higher frequencies, you can see that that is the same shape. That ODS is being dominated by a resonance, a single mode, and the MAC value is 1. And let me drag over here to another one. So all these other peaks in my data are a single mode. They're being dominated by a single mode. Over here, not the case. So just from the animation, we've got proof here that we've got closely coupled modes. All right, let's stop this animation, and let's go do some curve fitting and see if we can resolve this issue. So I'm going to take my PVC plate data here. We'll put it in the center of the screen. Let me close these boxes, and we'll put this guy away. And now we're going to go into curve fitting. So it says you've got things selected. In curve fitting, we don't want them to be selected, so we're going to unselect. Let me also display magnitudes. Again, a little easier to look at my data. All right, now we're in curve fitting. And under my mode indicator, I've got CMIF, MMIF, and multi-reference CMIF and MMIF. So let's go ahead and see what this mode indicator looks like. Oh, I got to turn my cursor off here first. In curve fitting, I have the cursor on. You can see it actually went ahead and built it for me, but I want to look at it over the whole. Okay, so here it is. Now the colors are a little hard to see. Let me go change the color to red. That's under my data block options box, and the colors are these contour colors. You can see there's that light green. I'm going to change that one to, well, let's change it to orange. All right, it looks like I need to rebuild it. Okay, so there it is. You can see the mode indicator, and it's going up and down, and there's some crossovers and so forth. But right over here in this range right here, let me put the cursor on over here. You can see that it's found two peaks. And there are two curves here because I have two references of data. Now, along with the eigenvalues or singularities, this is called a singular value decomposition, are modal participation factors that go along with these curves. And they're going to be used by the curve fitter to curve fit this data. Now I'm going to use the polynomial fitter first, and then we'll use the stability diagram and show you. So this is already set up with a multi-reference polynomial because I chose that indicator. And then if I come over here, the shapes are a multi-reference polynomial. So that's already been done for me. And if you're familiar with curve fitting in Emiscope, the quick fit will use this indicator, this method here, and this method here with a push of a button. So I'm going to just push the button here and let the quick fitter run. Bingo, it's done. It's found all the modes, and it does it by counting the peaks on the indicators. So the difference between this and a stability diagram is that we don't necessarily have to count peaks. We let the curve fitter find the modes for us. But in this case, it's a clear case of we've got two peaks over here, and we've got now it also found some rigid body modes down here. You can see the curve fitter is laying on the data. It looks pretty good. And but the proof of the pudding is not in the eating, but in the looking at the mode shapes. So let me just remove the two rigid bodies out of there. Well, let's save them all. So we've got two modes here. One, let me click here, and I'm going to zoom up a little bit. And you can see that I've got two modes, one at 187 and one at 189. Those are the ones that form this single peak in my data here. And over here is the modal participation for those modes. Let me drag this over in the spreadsheet so we can get a little closer look at it. So down here, let's just look at these two modes. You can see that they're participating in the two references a little differently. And this is what the CMIF calculation did for us. The 187 is minus 0.7 at 7Z, minus 0.7 at 35Z, whereas the 189 has got a minus sign in here. So they're, in a sense, they're at right angles. They're orthogonal to one another. And there's two different shapes that are participating in those two references differently. And then we can see all the other ones, the ones that were a single peak with a single mode, they participate basically 707 of one reference, 707 of the other. There's some minus signs in here, but nothing particularly different about them because they're not closely coupled at all. So let's go ahead and save those shapes, and I'll just create a new one, and we'll call them CMIF. CMIF quick fit. Okay, and let's put the curve fitting down. Let's kind of go back and rearrange things here a little bit, and I'm going to start the animation out of here. So animate shapes. All right, I'm getting that same dialogue again, multi-reference data. So it will not animate. All right, we're still in comparison here, so let's get out of that. We'll just go to animate the shapes. So there is the curve fit of the rigid body stuff. Not real good, but we weren't interested in that. There's the 187. That's the one. Let me slow this down just a little bit here. Okay, so there it is from reference 7Z. Now if I switch over and animate from 35Z, it didn't change. It didn't change. So again, I can do the same thing with the shape table that I did with the FRFs. Let's stop this. I'll stop the animation. Okay, well the animation stopped. I'm going to create a copy shapes to a file. I'm going to unselect. DOS are selected, unselect, and we'll just make a copy here. So now we got two shape tables, and now we can animate these different shapes and look at their MAC values and also look at their mode shapes. So let's start the compare shapes animation. Again, I'm getting the same question up here. That's for the CMIF, and it didn't change. Okay, we got quick fit. Over here it's animating. Let me just point you up here to the toolbar. You see the little blue arrow is telling me what's animating on the left. The red arrow is telling me what's animating on the right hand structure. In this case, I've got a copy of the model. No, what do I have here? I got the BLK copy, and I've got the structure, and I want the shape copy there. All right, it's going to tell me I need this. So now I'm set up. So now we're animating the two models. Let's go down here, and you can see that what happened to me. Quick fit. This keeps. Let me fix this. Side by side. Okay. Now we're good. And now if I switch to the next shape, You can see my MAC values are good, and I'm animating off the same reference. Now let's switch to a different reference here. You see how they changed? Now I'm animating off of two different references, and I've got the same mode shape, and I've got one at 189, and my MAC value is 100, and if I animate off the other reference, it goes to 187, and I'm on two different references, and I get the same mode shape. So that's what multi-reference curve fitting did for us. It sorted out those two modes that were at the same peak, whereas if we just animated the ODS from the imaginary part of the data, we didn't get a case like this. And then if I go down and animate these other ones, you can see that they all match up and this is from one reference versus another. So this is proving the point that I made, that the same mode shape exists in every row and column of the FRF matrix, if in fact it's a mode. Now if I animate ODS data right off of my FRFs and I don't see this property, then I know that there are two or more modes there. Let's go back to curve fitting. I'm going to stop this, and let's go I'm going to go over here under Windows, Open Window, BOK PVC plate. So here's our curve fitting. So this was the quick fit that we did. Let's go try one of the, and I need to shut down some of these dialogues. Let's go try one of the, I'll put these down too. All right, so now we're just looking at the data block with the curve fitting. I'm going to clear out. Let's keep everything. Let's get rid of these first two because those were the rigid body modes. And I'm going to go up here and say delete the selected mode. So here are 7 good modes. You can see the damping on them is quite different. The horizontal line indicates the damping of these two modes. If I zoom in around, or of all the modes, let me zoom around my double peak here. And there you can see the two estimates from the curve fitter. If I hold down I'm holding down the Alt key, it's showing me the value of the one mode and then the other mode. So I can look at that right on the diagram, and of course that all it's showing me is this data over here. Damping is similar but different, and we looked at the participation. Okay, so let's go and I'm going to go to my stability diagram, and let's try this multiple reference AF polynomial method. And we're going to let that one run. And you can see that it did a very clean job on this data. It's got very stable estimates. And again, it found the rigid bodies. And in here, if I zoom in here a little bit, I can see that it's got two modes in there. Now, what do I mean by that? Well, when it colors them a different color, that means they're part of the same stable group. So the orange ones all had frequencies and damping within these tolerance. There were at least 5 of them in the group, and anything over a damping of 40 hertz was ignored. So these are tolerance limits that I can set in defining a group. But you can say with this data, very clean, the curve fitter found very good results. And so I need to save those results, and I'll say save the groups. Now we have 2 sets of curve fit results here. Let me order them so we can kind of compare one set from the stability diagram and the other from the quick fit. And I'm going to go up here and say order these. So now we can come over here and look at the difference in the curve fitters. You can look at frequency and damping. You can look at the participation, slightly different. But if you compare the the 187 with the 189, very similar results, and then so on down the list we've got a comparison of those mode shapes. So again, let's go ahead and save those. These are the selected ones. Over here we can look at the fit function just to verify. We haven't looked at a fit function here, so let's just put one up. There's the fit function for the selected modes. Again, very nice job. So we're happy with that, but don't let fit functions fool you. The mode shapes are what we really want to look at and compare them with a modal assurance criterion to see if we've gotten the same results. So I'm going to go ahead and save these. This is going to save the selected ones. I'll create a new one and we'll call it the stability modes. Did I spell that right? All right, I'll put this down. Let's put the stability modes up there. Let's go get, I need to go over here and under my open windows, I want to open up the shape quick fit data, and we'll put that down here, and I'll arrange things and start the animation. Compare shapes. Now I need to look up here to see what I'm actually animating. Okay, quick fit is on the left and shape copy is on the right. I don't want that. I want stability on the right. All right, it's telling me I need to pick a reference. Now down here it already had a reference chosen, so it didn't put up the selection box. I can put that up manually because it only looked at my selected DOFs and said, well, you only have one reference here. Let me go ahead and put up that box for selecting DOFs, select by, and I'm going to say by its reference DOF, and there they are, there's two of them. So now I have that box up, and they're both animating from the same reference. And you can see that the two curve fitters, again, the animation is still comparing them by frequency. Well, this is the 500 hertz. Let's go up here to there they are. There's the two bending modes, and they're 99% the same, 98% the same from the two curve fitters. But they're both off the same reference. So let's change the reference on the stability data. Now we're animating from the 35Z. And it didn't change. We still have a mode shape that's exactly the same. There's the torsion mode. So again, I was looking for first bending. There it is. I was looking for first torsion in this data. There it is. They're only 1 hertz, 2 hertz apart, and the curve fitters extracted the mode shapes from this data. So that's enough of that example. Let's go on to the next example of repeated roots. Now these are both in application notes, so that if you're an Emiscope owner, and I think most of you probably are, you can go and I'm going to close this project. Close the project. Do you want to save any of this? Oh yeah, we'll save it all. And I'm going to open up application. That was application note 15. If you go to our new website, you can download that application note and go through this same exercise yourself. Now let's go to application note 14, repeated roots, more complicated curve fitting example. Let's look at some mode shapes here first. I'm just going to start the animation. Let's see, I'm pointing. See up here in my animation source list, I'm pointing at the, I've got a BLK, I've got a shape table with Z DOFs only, so it's just vertical. So I'm going to point at that, and that's this table here, Z DOFs only. These are, let me make this larger. These are FEA mode shapes. So we actually built a model of this plate, and you can see in here that we've got a lot of repeated roots. Same frequency, same frequency, same frequency. There's pairs of them in here. Let me make this a little larger and we can see them better. You can see just lots of pairs of repeated roots in there. Now we've given them, because they're FEA, we've given them all 1% damping. So typically in FEA, even though in Emiscope you can add proportional damping to your model, we didn't do it in this case. We simply went in and inserted 1% critical. You can see that the damping in hertz is different, and down here are some FRFs that we synthesized from that data. But let's go ahead and animate. I'm going to start the animation out of here. Doesn't matter. I can start it on either side. And again, if we make a copy and we, now this is multi-reference. I mean, this is single reference here. Let's go look at this data. Let me put this down for a second. And we'll just look at the, you can see DOFs, when they come out of the FEA solver, there is no reference. The reference is only used when we curve fit FRFs. And we know that an FRF has 2 DOFs. Out of an FEA solver, we only have a single DOF. So you can see the mode shapes here have 160 degrees of freedom at 160 points in the Z direction. That's what we're looking at down here. Scroll that down a little bit. Let's make a copy of this. Again, I'll stop the animation. Draw. Put it back into draw mode. I'll make a copy of this one so we can compare the two different mode shapes at the same frequency. I'm going to go edit, copy shapes to file. It says you got shapes selected. I want to copy them all. Remember the rule in Emiscope, if something is selected, only that would be copied. In this case, I want to copy them all, and I'll make a new table of called copy. So let me rearrange these, same as we've been doing before, and I'll pull that down there a little bit. And let's start up the comparison animation now. Now remember, as soon as we start comparison, okay, source has multiple references. See, it's pointing at BLK 5Z, 15Z, 25Z. That's what was left over from the last time this was running. We don't want to animate out of there yet. So I'm going to close this, and we're going to select, let me start it up again. And now we'll go over here and select the copy to animate on the right. So there we go. Now you can see here we're animating the same frequency. So I don't want to necessarily compare them by frequency. I can compare them by their MAC values from table to table. In this case, though, I don't. Let's just click down here, and you can see there is the other 108 hertz mode. Up here is 108 hertz. Down here is the second 108 hertz. You can see the MAC value is 0 virtually, which means that these shapes are totally different from one another. And you can see from the display that clearly they're a different mode shape. It's the same looking mode shape, but one is rotated away from the other. So let's go down here at 200, and then at 200. So there's the 200, and that's the same mode shape coming out of those two shape tables, 100%. Now let's go to the 282, and down here, 282, there's the same mode shape. But now I go to the other one, and the MAC value drops down because it's a different mode shape. Let's do that one more time. I'll go down here to 397, and I'll go down here to 397. MAC value is 100. That's the same one. But then if I click on the second one, the MAC value goes to 0 because that is clearly a different mode shape. Same looking mode shape, but rotated quite a bit. So these are repeated roots. Now what we did is we synthesized some FRFs from this data. So a little bit of a contrived situation, not a realistic measurement situation. In fact, if you had a disk like this that you were making measurements on, you'd probably want to upset the symmetry a little bit by maybe putting a small mass on it so that the modes would separate a little bit and you wouldn't get repeated roots like this. But let's just go ahead and look at the curve fitting results and see what the curve fitter is going to do with this data. So here is our data that we've synthesized, with this time with 3 references in it. Now, since we've only got repeated roots and we're looking for 2 modes at a particular frequency, 2 references would be good enough. But just to check out the curve fitter, we created FRFs with 3 references. So you wouldn't necessarily know how many repeated roots you had in a test situation. You can always test with more references, and the curve fitter should tell you whether in fact you have closely coupled modes or repeated roots, because the additional CMIF curve will show it to you, or the MMIF. We didn't actually try that one. All right, let's look here at the points just quickly. Let me put the point labels on. Okay, so here's all of our test points, or in this case the FEA node points, and we created some data here with references at 5Z. Well, let me put some of this down here so we can see things better. We'll just put this thing up here, and we could animate this data, but since we're running short on time, I'm going to just go right into curve fitting it, and we'll look at, but here you can see we've got how many measurements? 480 measurements. That's 3 times 160 because we got 3 different references of data. Let me make this a little larger so you can see that. We've got one reference at 25Z, one at 15Z, and one at 5Z. So where are those 3 points? Let's go see if we can just light them up quickly. And so I'm going to switch over here to my points, and we'll just turn on point 5, point 15, no, 15, and point 25. So those are where, if this was a roving impact test, those are where we would have the 3 accelerometers. And I could create little icons there to show those. I didn't do it on this model. Those are our 3 references, though. And so let's put this down, and here is our data that we created with the mode shapes, and here it is over a 1500 hertz range, and you can see some peaks in there. So let's go into curve fitting, and modal parameters. Okay, it says you've got things selected. We're going to unselect everything. All right, well, we already got some stuff in here. Let's go back and clear everything out. And here we are with a clean slate. And I'm going to come over here and use one of these indicators. Let's look at the multi-reference CMIF indicator. It's using the imaginary data. Again, that's the best data for acceleration or displacement. If I have velocity, I would use the real part. Now you can see that it's counted 19 peaks. And that's exactly right. We had 19 modes in there. And you can see that here's a repeated root. There's 2 peaks there. Let me zoom in and we'll just walk through this a little bit. So there's two peaks there. There's a single peak at 200 hertz. That's the single mode. There's a repeated root there. There's a repeated root. And you can see that all these higher frequency modes are repeated roots. It's counting them as repeated roots. So 3 references of data, 3 CMIF curves, and the ones that rise up out of the noise and show us those peaks are the ones that are indicating repeated roots. All right, let me run the quick fit on this. We'll use the polynomial. Again, quick fit is always my favorite if it works. If there's problems, the other advantage of quick fit is you can set the band cursor on and just go in and quick fit in a small band. Now, stability doesn't work that way. Stability, and typically got to use wide bands. Anyway, here we are, the fit function right on top of the synthesized FRF data, and of course it's ideal data, so the curve fitter did a very good job. Let's look over here at the modal participation now, and well, let me drag this over so we get a little closer. And now I'll zoom it, and let's reset it. So now we can see how these repeated roots participate at each of these references. You can see they're just different combinations of the data. And go down here to 282. This is how the curve fitter is able to distinguish one mode from another by sorting out based on these participation factors. And all the way down you can see it's found all the repeated roots. And so let's save those, and let's just try the other mode indicator and see how well it does. So I'm going to go ahead and save these shapes, and we'll call them we already have something called CMIF, so let's just go ahead and save, and I'm going to do a replace then, and I'll replace. So now I have a shape table with those mode shapes in there, and now let's try the other mode indicator. I'll put this down, and let's clear out everything, start over again, and let's look at the MMIF and see how it does on this data. Okay, so there it found 19 peaks too. You can see that the indicator is a little different looking, nice and clean. The peaks are all up there around 1. That's one of the advantages of this method. And again, if I zoom in and look at how it found the peaks, well, they're just laying right on top of one another. I can't even see them. Over here I can see 2 peaks, but here it's counted. There are 2 peaks there. There's 2 MMIF curves, and so the curve fitter is going to use that information to go ahead and do the curve fitting. I'll just do the quick fit again. And there it is. You can see it did a pretty good job. The fit function is laying on, and in most cases there's a little bit of an error there, but we can go through and look at these mode shapes here, and the participations may be a little bit different. You can see it's getting pretty complicated here. Let me go ahead and save these, and we'll call these the MMIF shapes. And let me put this down. Let's just see how these 2 curve fitters did, whether they got the same answers or not. Open windows. I'm going to get the circular plate up. Open windows. Let's get the CMIF data. I'm going to rearrange things here. And okay, so there's our model. There's our 2 shape tables. Let's start the animation, and we're going to do a comparison again. Now we got points on here. I'm going to turn off the point labels and the points, and maybe put on the surfaces. And so we're animating we want to animate MMIF there. Okay, it's multi-reference data, so it's telling us MMIF. I'll put that down there. And then on the other window, I don't want this shape table. I want the CMIF results. Again, I need to put up the dialog box. So here we are. We've got 3 reference sets of data. Let me pull this over here a little further and rearrange. You can see what I'm using a lot of the controls here, which hopefully you're familiar with. The last window that I touch will keep its size when I hit this arrange for animation. So if I pull this way over, well, here, let me grab this one and pull it way over here. That's going to keep its size, and the range will move everything to fill in around it. So there we are. Here we've got 108 hertz. Now let me see if it switches. No, it doesn't. So you can see that dropped way down. But if I go to 108 hertz here, that's the same mode shape. Let's switch the reference here to 15Z. And you can see as I switch the reference on the CMIF data, and I'm animating with the first reference on the MMIF, the MAC value stays the same. So there is evidence of a mode shape. It doesn't matter which reference I animate from, I get the same mode shape. Same thing down here. I can switch down here and animate from a different reference, and I still have a MAC value of 1. I still have the same mode shape. And so what this is showing me is that the curve fitters, both these indicators, using their modal participation, the quick fit polynomial fitter went through and got the same mode shape for each of, or from each of the references. So it's 9:30, 9:40. Maybe we should take a break here and answer some questions. I've got some other examples, but to keep this to an hour, let's just see if we can handle some questions now. Oh, no questions. We'll give you a minute if any of you have questions to send in as emails. We will answer them. We can go back over these 2 projects. We've got another project. I guess to summarize, you can always use multiple reference data to your benefit to make sure that at a resonance peak you only have a single mode. And so if you have a structure, and typically it's usually the case that each resonance peak is evidence of a single mode, but if you take the multiple reference data and you use the animation like we're doing it and then go in and use the multiple reference curve fitting, you can extract closely coupled modes and repeated roots from your data. Okay, well, we didn't have any questions today, so I thank you all for coming. We'll probably do this again next month for those that weren't able to attend today, and I certainly welcome you to come back next month, and we'll do it again, and maybe you'll have some more questions. As I said, these 2 examples are application notes that you can open from our website and go through this exercise that we did here today. So thank you again and have a good day.